I hinted at the fact that you can construct a heap in constant time from an established list of data. This is called bottom-up heap construction, and it does require the array, the data to be in an array. But if we have that, we start with our data in that array, and starting with the last internal node in the array and stopping at the root, we reheap on itself and its children and then move to the previous internal node. How do we know what is the last internal node of this tree? What is the last internal node? Well, the last internal node is the last node that isn't a leaf, which is this guy. Well, what's the position of that guy? How do we know where that is? Well, we just find the last element in our heap and find its parent. That's it. Right? It's always going to be true. If we had another guy, well, hey, you know what? We'd find that element and we would find its parent. And this would be the last internal node. This is always going to be true. The parent of the last leaf is the last internal node. So we can go, cool, 8 minus 1 integer division of 2. Hey, that is 3. And a thunderstorm. So from there, we can just start reheaping. Okay, so I'm sure you don't believe me, so I'm going to pick something that's probably poorly organized. 7, 3, 5, 1, 2, 8, 7 again. Let's get rid of that. I was going to say 4, and I got tripped up. 4, 0, 1, 2, 3, 4, 5, 6. 9, 3. I have no idea, right? So there we go. Index 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, beautiful. So 8 minus 1 integer division 2 equals 3. And I'm going to move off of this terrible color in a second. I'll go to purple. Oh, I'll go to black. Black is good. So index 3. So let's start here. Right? So its children are, right? We go womp, 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 right? So we can see this makes sense. So let's get rid of all those combed over hairs. Okay. 9, 3. Do we need to swap either of those? No, we're fine. So let's move up 1. 5. Well, let's see. Its 2 children are 8 and 4. Do we have to swap anything? Yeah, the heap order property is wrong. 5 and 4 need to get swapped. So 4 goes here, 5 goes here. I'm sorry, 3 goes there, 5 goes there. Cool. Now let's move up another 1. Now we're at 3. Who are the children? Hey, it's 1 and 2. Well, do we need to swap? Yeah, we do. 1's got to come up here. One and 3. Cool. Okay, now we go here. Hey, do we have to swap again? Yeah, we do. Oh, we need to check here, by the way. We need to keep going with 3. 3 goes 9 and 3. Are we in good shape? Yeah, we're fine. Okay, so 7, we do the same thing. 7 and 1 need to swap. I'm going to be real upset if I lose power right now. Okay, now we go 7. 7 goes times 2 plus 1 is 3 and 4. Do we have to swap? Yeah, we do. 7 and 2 have to swap. Okay, 7 times 2 plus 1 is 9. We're off the charts. We don't have to worry about it anymore. So let's see. Do we have a heap? 1, 2, 4, 3, 7, 8, 5, 9, 3. That is a valid heap. So that's how that works. What's the big deal? Well, the heap can be constructed in place without needing to add additional memory. And it's way more efficient to create it this way because we can assume that the leaves are in order. And remember, when we come back here, right, everything to the right of that line is a leaf. We had an array of 8 as well. So we are just starting off assuming that half of our array is already fine. We don't have to do anything for that first half. And then the first level of leaves, the first level above the leaves, we process half of the remaining nodes, but we only do a swap of 1. Then the next level above that, we process half of the remaining nodes, and we do a max swap of 2, and so on and so forth. So this means that our heap creation can be accomplished in big O of n time because we're doubling the number of potential swaps, but we're having the number of times that we need to do it. So we can compare this with top-down heap construction. And we can say, okay, well, we've got n elements, and each one can be inserted in log n time. Well, that's n log n runtime. We can complete our, we can create our heap in a computationally truly faster amount of time by using bottom-up heap construction.